This is Interviews with Technical People with John Robertson,
And James have you
a podcast where we interview technical people in STEM fields
to discuss the past, present, and future from their perspective. Today we are joined by Onur Danaci. Onur is a physicist and a computational scientist specializing in quantum optics, quantum computation, and machine learning, working at the IBM HBCU Quantum Center based in Howard University, Washington, D.C. Onur, welcome to the show.
Thanks for the kind introduction, James.
So we are thrilled to have Onur with us. I will say, for those of you who don't know, I got my PhD in physics from Tulane University, and we were just talking about this. Onur is actually the first of my co-graduate students in physics at Tulane to come on the show. So that's really exciting. So
I am honored.
yeah, there you go. So, and we've hit a lot of topics, but now's the time. We're going to hit some heavy physics, everyone. So everybody listening, get ready.
Buckle up.
This is the real deal. So, Onur, the way we often like to start is I'll just ask you the question of what do you do?
Mhm.
In your own words.
This is actually a good question to give some good introduction, I think. I mean, in broader sense, like I'm doing computer stuff. Like I'm mostly on my computer. So meaning like I'm analyzing data, I'm making simulations, and combination of both.
Mm-hmm.
I'll explain to you shortly. So that's what I do. But like in terms of the topics, my main interest is quantum world and their applications. So like the late John Dowling, the supervisor of my supervisor, so he coined the term quantum technologies. So this is the broader field that I'm interested in.
Quantum technologies. Okay.
Is that basically a way to take quantum physics and incorporate it into technology and, processes in our daily life? Or
More or less. So it's I would say like it's more like an umbrella term for the new coming technologies that are things like quantum computing, quantum cryptography, communication, and like for example, quantum internet, etc. So you haven't heard it yet much in the popular science or I don't know in the newspapers, but like I think you're gonna be hearing more. So there's basically some sort of like space race between I don't know United States, Europe, and China for like who's gonna get the holy grail of like quantum internet, for example. So you're gonna hear a lot about it.
So I think this is interesting because James and I know a little bit about quantum mechanics, and I've often heard the term quantum computing, and we would love to hear you explain what quantum computing is.
Definitely. As I would say, so I got into this field like when I was in undergrad, like let's say in my senior year or maybe sophomore year, and like I started going to these workshops, summer and winter schools, and like conferences in Europe. And by the time I started, so people were somehow cynical because like this quantum computing and all those related technologies, they were hyped a lot in 1990s, and people were expecting all this short gains. Like people are expecting like just in 5 years, like we're gonna have this, we're gonna have that, but they didn't. So that's why by the time I was in the field, like people were pessimistic. They were like making jokes about so we are not getting there, we're not gonna get it. But right now things are changing.
And interesting because that was many years ago already, right? And so
Yeah,
now it's already been another 10 years or so.
exactly.
Yeah.
So we are at I don't know. So at this point, like we are getting higher. I would say, like I got into field when like we were at the dipping point when people were pessimist. Now we are at the optimist position again.
And what is the promise behind this technology? What can it unlock if we can discover the secret?
Um, Also a good question. So because it's not like a I don't know, magical key, like a philosopher's stone for everything, but like it's gonna revolutionize some computational problems, but not all. Like your desktop computer, your laptop, your high performance computer in a cluster may perform. Your classical computer may perform some tasks still better, but like for some certain tasks that are impossible to be solved by so-called classical computers are going to be realized by this quantum computation. So this is the promise of these
Hmm.
technologies, and also this is how these so-called quantum technologies started getting funding from government agencies from and at the moment like they are getting like funding from huge tech industry partners such as I don't know Google, IBM,
Mhm.
especially. But this wasn't the case before, so there had to be some time to convince everyone in the field, like all the top shots. But now we are getting there. They are already convinced. Now we are taking some steam.
Is it that quantum computers are able to work so much faster or so much more in depth, or what makes them better computers for certain problems?
Um, okay, let me give you an example. So this is the most well-known example. So let's say you are trying to separate a number into its prime number constituents. I mean, very simple example. Let's say number 35, right? It's like 5 times 7 is number
Yeah.
35. And but like let's say you have like a huge number, let's say 3,600,000 yada yada, like, and you are trying to just get its prime constituents, right?
Okay.
It's almost impossible. That's why the most of the modern cryptography technologies, even let's say you are using like WhatsApp or something, and like you are trying to send like an encrypted message, or like you are shopping in Amazon, or like you are voting in a booth, using a voting machine. They are using like this encryption technologies based on this very simple algorithm, right? But for example, for this task, quantum computers are I don't know, like instantly breaking it. There are like algorithms that would
Hmm.
only run in this type of computers that would be instantly breaking this kind of like encryption codes. And like in the 1990s, like some I would say some people in Department of Defense, they just realized they are like shoot, like we need to do something about it. We need to take the first step, and they started giving the funding into the researchers, and rest is history. So,
Hmm. And here you are now
and here
working
I am.
the same problem. um, I have a question,
Mhm.
and maybe this pertains to how, like, what the technology actually is. But just to use as an example, what I think I would consider to be a traditional computer, like
Uh-huh.
the fundamental base unit of it is a semiconductor transistor, right? That can
Mhm.
flip on or off, so it's binary. It's a one or a zero, and
Mhm.
then in combinations of ones and zeros, we create all modern computing. Does quantum computing use that same system, or is it fundamentally different from that?
It's fundamentally different. Like I would say, it's a different paradigm.
Okay.
Like so, this uh, philosopher of science, Thomas Kuhn, like when he first talked about this paradigm shifts, like the how
Hmm.
different paradigms, he was saying that like some concepts in the previous paradigm is like incommensurable with the new one. So I would say like we still have some sort of a bit, but it's kind of different. So it's almost becoming like a cliche right now. In quantum world, we have like this quantum bits, which is the combination of this zero and one, just like the Schrodinger's cat.
Okay.
So this is what we have. That's why I would say it's not exactly a bit, but like something in between. Just like whenever you are not looking to this Schrodinger's cat, it's both dead and alive. but as soon as like your act of looking at it either kills it or keeps it alive, but like that's not what we want. So quantum world wants to keep you ignorant of the well-being of the cat. So it's basically computing on the uh, I don't know, in this weird quantum superposition state. In other words, like Schrodinger's cat both being dead and alive at the same time. So this is
Interesting.
it is.
Yeah, and this is where quantum mechanics got so mysterious. I know for people like me and probably James, where it's getting into this mindset of no longer working with discrete, ones and zeros, but these probability densities
Exactly.
of what could be occurring.
I'm wondering how you use those probability densities to solve problems. I mean, that's the practical part that I'm not quite seeing from it yet.
Yeah, right. Like, are there physical machines that exist that do this, or is it theoretical
Yep.
at this point?
Maybe a couple years it will be still theoretical, but right now, like it's promising. Like, for example, like right now, like Google has its own quantum computer based on superconducting qubits, and IBM has one, and IBM also has like some sort of open source software that you can use it to access and program quantum computers.
Yeah.
For example, through my fellowship, like I have access to this quantum computer,
Wow.
and I'm gonna use it to do some cool stuff. The tomorrow I'm gonna have like a very good I would say very fun meeting. I'm super excited about it. So there is this African board game named Mancala.
Oh yeah,
Uh,
I've played it.
you played
Oh,
it, right?
Yeah.
Yeah. You can have like egg carton and like two balls, and you can even play with it. So, for example, like one of the first projects I'm gonna be taking on is playing Mancala using a quantum computer, getting like some sort of quantum AI to play against the player. Uh, you can even start doing that kind of tasks.
so what does a day look like for you as someone who's working in this field? What kind of tasks do you do to move the boundaries of this field forward?
Yeah, good question again. So I would say uh, a lot of elbow grease, of just coding and lots of trial and error while before doing simulations, like creating toy models. And like let's say you are trying to solve a three-dimensional problem, you first solve like the simplified versions, even though they don't have any practical use. Uh, so keep building physical models, keep building statistical models, and keep on simulating. So this is my everyday life looks. And also like as a scientist, I have to do a lot of writing. It's the not
Yep.
so fun part about it.
I remember that. so so you're just working with probably very large code bases, probably some of which, like, how much of this is home built by you versus are you using other open source libraries and things of that nature?
And what sort of programs and languages are you using too?
Yeah.
Um, Good question again. So like I'm using I mean for the machine learning tasks there are you can in principle write your own code, but like it would be high unnecessary because
Yeah.
it would be just I mean I did it, but like it's not necessary. I'm using uh, some open source programs like the libraries developed by Google and like
Hmm.
also Facebook, for example, TensorFlow, Keras, and they are very easy by the way. Like there's like when people talk about machine learning, it sounds super mystified, but I would say if you are I don't know, let's say you are 20 years old, you just know you are just a novice at programming, even you can just start doing something and like you would develop some intuition while working on it. So there are like some programs like that are like more you develop some intuition as you are going through it, like this machine learning software, but like also like for some other uh, computational software such as, I don't know, MATLAB or like some other Python libraries for doing just linear algebra. Maybe it requires more knowledge of numerical computation, I would say. And what else I'm using? Like I'm using some for making like parametric calculations, such as, I don't know, a plus b equals c. That kind of parameterized calculation I'm using like a Mathematica,
Hmm.
Wolfram Mathematica, and what else? And for quantum stuff, there are IBM's Qiskit. This is what I was talking about. Like you basically connect to a IBM quantum computer through it.
Hmm.
And also there for different type of quantum computation I'm going to get through. There's this Canadian-based company named Xanadu, just like in sci-fi, Xanadu.
Oh.
They have like some couple software. For example, I think they have like Strawberry Fields, just like Beatles song,
Mm.
Yeah.
and they had another one also Beatles song, but I can't remember. So these are the libraries and like I don't know, softwares that I'm playing with. And I used R too. So when I was doing some sort of computational data science biology internship in a genetics lab, I was also using R, the statistics software. But mostly, I would say, just like Swiss Army knife, Python is the king. It is everything. It is open source. I love Python.
Yeah, and I'll take a brief moment and second that because I've also needed to start using Python recently because I think it is the king. For those of you who don't know what Python is, it is a programming language that is just very, very versatile. And as Honor said, it's open source, meaning you don't need to pay to use it in general, which is really nice. So any of you at home can go pick up Python right now and start using it.
Exactly, and you can. They can even. I mean, our listeners at the moment, even right now, they can just download it. Like there are clear instructions, and like without
Mm-hmm.
even downloading, they can just start playing online. There's something called some interface called Jupyter Notebooks.
Mm-hmm.
I would say like if I am to talk a 20-year-old, I have a brother who is 20 years old, and I keep poking him, like telling him, okay, learn Python, learn Python. Hey, are you still learning Python? You are not learning Python? Come on, just learn Python. So yeah.
I remember being told the same thing when I was that age, and I didn't do very well at learning Python, but
Well, Anna, that's another question I wanted to ask. So you said you first kind of heard about these topics when you were a senior in college. Now,
Mhm.
how quickly or how long did it take you before you were able to get all of these various tools ready to where you're able to really make some progress? Did it take years or was it fast for you?
It was rather fast, but like to commit into fruition, like so, it depends on your metric. Like so, I was able to understand concepts. I was able to do some simple simulations or like some calculations on paper, and I don't read the papers, but like up until I write my own paper, like it took some time because like that's why I'm saying like it depends on the metrics. So if you are in industry, probably like you could just learn in like maybe 6 months.
Hmm.
But like if you are to write a paper, like academia is different. I would say like in projects in academia are also like the scale and the I don't know. Like I would say there's a huge difference, but like to do anything productive, 6 months is more than
Huh.
enough. In my case, like what helped me on top of my the courses I was taking in my undergrad, I also went to some winter schools, summer schools, and like I didn't pay a dime, by the way.
Hmm.
So I would if I'm 18 years old or 20 years old, I would just try to find all those good opportunities, and I will just shoot the organizer an email. I'll try to get some funding. So, for example, in 2010, I went to this 1.5 month winter school in Italy. It was in this physics institute in Trieste, Italy, northeast of Italy, and like the United Nations basically paid for my flights, for my lodging. They were giving me food. They were giving me some, I don't know, not salary, but like some sort of stipend, like albeit small. And I don't know, like that kind. I think people can just follow this kind of opportunities, and usually, they make a huge difference. And I was meeting some people, they
Fantastic.
were telling me, even though they are not presenting some stuff, maybe it's a good idea to just go to conferences, workshops, to seminars, because like I don't know, like I would say from my research experience that like there may be a problem that you are stuck for months, maybe years, but like if you are just having beer with someone in just 5 minutes, just casually they could just give you a tip, and then suddenly you are like eureka, right? Like it happened to me like before, like I've been stuck in this problem, but like just being in the same place with the I don't know, scholars, like the people, the experts of the field, they just give you like a lightning boost.
Can you tell us a little bit about some of the papers that you've written?
Yeah, sure. That's a good question. And also like reminding me that like I still have some papers that I still need to publish. I mean, they are ready, but like I haven't submitted them.
I I remember those.
Yeah, they are like itch behind. Like you always, for example, I got a master's because like in my country and like generally in Europe, usually you go take a master's before you start PhD,
Right.
unlike the United States, and it's for free, by the way. And for example, I have my work, my thesis, but like I started my PhD over here super fast. That's why I didn't have time to publish my
Hmm.
master's thesis.
Oh, interesting. So unpublished work from your master's
Exactly.
time.
Starting with
Oh
my
man.
unpublished work from master's, it was quantum control of metamaterials. And so it's about like you have some sort of weird optical device, I would say, like that is like just layers of like different materials. And if you want to do anything, something quantum with this kind of optical, I don't know, not material, maybe optical device that are prominently used for many applications. How would you do it? It was my thesis and my unpublished work. And then when I came for PhD to Tulane, then I started working on this field, so-called nonlinear optics. And our listeners might ask, what is linear? What is nonlinear about optics? So very briefly, let me tell you about it. So linear optics is like when the systems you are interacting with also gives you some sort of linear response, like some adequate response, for example. And this response is not depending on the intensity of the light interacting with this. I mean, the brightness, intensity means brightness of the light interacting with this physical systems. I mean, for example, just everyday life, like mirrors, if you have glasses, lenses, they are examples of linear optical systems. And nonlinear optical systems is like when I mean, let's say you have some sort of a glass, and then let's say you keep increasing the brightness, and for a while, like it's just acting normal, but like when you exceed some threshold, it suddenly starts acting weird, right? Like this is the nonlinear part about it. For example, lasers are nonlinear optical systems because you send some light to it, but then, and it amplifies it and gives you a better light, right? So this is something nonlinear because you are creating something. And nonlinear optics is about it. So I was working in this nonlinear optical systems based on something called four-wave mixing. I'm going to explain what four-wave mixing is. It definitely includes
Okay.
mixing of four waves, as the name suggests. And so why are we interested in this? Because of the quantum implications. And I'm gonna come to that. So first again, like, what is this four-way mixing? So you send some bright light on this tube full of rubidium gas, and you don't need to know what rubidium
Okay.
gas is. I still don't know what rubidium gas is. I just have this system, and I just have to deal with it shortly. And so you basically send this bright laser light to it, and then you send another not so bright laser light in different color, and you suddenly create like the twin photons. So, well, and like what I'm trying to say is that, like, let's say in the left hand port, you are creating a photon. Then you know that, like, in the right hand too, it heralds that you're gonna have another photon, and they are correlated because they are coming in twins, right? Like, you create one photon, two photon is a couple or three photons in the left and right hand port. So, and I had a paper on this system in 2016, and we were most interested about, like, whether we can send some sort of, like, instead of just uh, I don't know, some round shaped laser beam, like laser pointer light, instead of sending that, maybe we send funny shaped, like the, I don't know, maybe bullseye pattern shaped, or like some picture shaped laser light. Like,
Hmm.
how are we gonna get, what kind of pairs of photons are we gonna create through that systems? And so I worked on that kind of systems, and recently I extended my work on those systems to, I would say, for quantum communication.
Hmm.
And by that I mean, can use that correlations between these paired photons for, let's say, to securely send a message.
Okay.
I'm gonna get into the details of it again. And
But so real quick, I just have a question. If we can clarify about these coupled photons.
Mhm.
So you noted that there were two in this example, two light sources, right?
Mhm.
One more intense than the other.
Yeah.
Is the coupling of the photons between one photon from each source, and they're coupling together because of some initial conditions that are provided? In other words, what's the nature of the coupling? If you can get a little bit into that.
Mhm.
And again, for the listeners, when we say photons, we just mean a quantized energy package of light. So it's just a way of, like, if we assume that light is a particle, it's like a particle of light. So that's what we mean by that. But can you just go a little bit into that?
Sure. So let me take a step back into this four-way mixing. So in this four-way mixing,
Okay.
you send, let's say, bright red light. And, like, this is something
Okay.
called pump. So you are pumping this is like a pump laser. So sending, like, very bright light. So you are annihilating two light particles, two photons from this bright light, pump light. And in exchange, you create one photon in the left-hand port, also called probe, port of the light, and
Hmm.
another one in the conjugate port. So they are twin photons, or sometimes they are called, like, signal and idler, or I don't know, some different communities, like, I don't know, chemists, or like some different engineering communities use different names or in different
Hmm.
contexts. But we were calling them probe and conjugate. But, like, the point is, like, since you are annihilating photons of this bright light, the photons you need to create must have like their energies equal to the created photons should have the equal energy as the annihilated photon. There's like some sort of transformation.
When we say that this is a four wave mixing, I think I counted three waves there, right? So the photons of the source or the pump, and then two resultant. So is there a fourth, or is that the
Good.
wrong way to look at it?
This is actually a very good question. Like these were the things I was initially avoiding, but just like this Russian dolls, it's it keeps opening like a gift keep on giving, and so in quantum world, maybe let me give you an example. So there is let's before going to nonlinear optics, let's go back to linear optics again. So in
Right.
linear optics, there is like I was telling you about, like for example, we had lenses, we have mirrors, and also there's sometimes like you when you don't polish the your mirror, you create something called beam splitter. So this beam splitter is like partially reflective and partially transmissive. So this why like when you shine light on it, like some are just going through it and some are just reflected. And what does it mean is that like let's say most of the time they act on something called polarization. So it means that like how the electric field of your light, I mean, where in which direction they are pointing to, it's not super important, but like basically it split the light, as the name suggests, like the beam splitter,
Beam splitter,
right?
yeah.
Let's say you are sending like the 100 photons. Let's say it is a 50-50 beam splitter, like the 50% would be just transmitted, another 50% would be just reflected to different direction, right?
Okay.
But the quantum interpretation of this system is quite different. I mean, I wouldn't say interpretation like because I would say the quantum world is the more fundamental one. We are living in a quantum world. That's why the real nature maybe is a better word. The real nature of this beam splitters are different, because in quantum world, I told you like you have this input light, right? And it's either transmitted or reflected. But like in quantum world, like you need to think about the vacuum. In other words, nothingness also as an input. Because like you have like you have like the input light and output light is like let's say transmission and reflection, right? And but in quantum world, you think about like the input transmission port, input reflection port, and output transmission port and output reflection port. And you can see this in the lab like super like easily, and because like vacuum is always there, like the vacuum fluctuations, like they haunt you, like in very simple atomic processes, like you see this quantum fluctuations, like you see it as a noise. Let's say you are trying to send some signal through a satellite, like they affect your transmission, like these vacuum fluctuations, because everything is quantum, nature is quantum. And just like that, just like a beam splitter having one of the ports seemingly unoccupied, is actually there's actually a vacuum, like the universe's nothingness is there as an input, like the zero photon, like no photon is also a photon. This is weird, I know.
Interesting.
That is very interesting.
Just like that. That's why this four-way mixing is still four-way mixing, because I told you about it, right? Like in four-way mixing, what are mixing are actually not the pump, like bright pump photons driving it that we are annihilating, but actually what we are talking about, we have like the input probe photon, input conjugate photon, and output probe and output conjugate photon. In most of the time, like there is nothing But like in quantum world, nothing means actually there is vacuum there, just inducing it. It's weird, I know.
which is also, but yeah, and this is farther than I ever got into quantum. So it's interesting to hear, though. Well, anyway, I think that does explain the question that I had. So
Let me give you a good example. So, like, what is the applications and
yes,
implementations of this? Um, so, let's say let's say you are on a Christmas break, and then like suddenly you lost your sleep. You are 10 years old, and you turn on the TV at 3 a.m. in the night, and you realize like the cable TV is gone, and your TV is like making this noise, right? Like there's like this white noise on the screen. There are like it's like snow. Each pixel is like I don't know, one is off, one is on, right? So this is something called white noise. And this white noise, one particular type of this noise is called, like in electronics jargon, is shot noise. So meaning, uh, let's say you have a laser light, and this laser light, let's say you subtract this light from itself. There are like some ways that like you can use some electronics, so that like through this like you can this you measure signal A, you measure signal B, and through this electronics you can just subtract the signal of A from the B, right?
yes,
And like even though they are the same light, and then you are expecting like, yeah, I'm extractory, I'm just taking the signal from out from itself, I should just have zero, right? But no, like because this signal, this light, since it has noise, at the end, like when you subtract it from itself, you don't have zero, but you have noise again. You subtract noise from noise, you also have noise. But it's getting weird with the quantum world. Like I mean, for most of the time, like let's say I would say for a classical engineer, this noise is a nuisance.
yes,
But like for a quantum engineer, uh, it's not a bug, it's a feature. So you are engineering that noise, because I was talking about this shot noise, right? The white noise of the normal laser light. You subtract it from itself. It has something called Poisson, like a named after a French mathematician, Poisson statistics, and meaning that like when you have like shot noise, most of the time they compare it to, let's say you are in a wood cabin and it's raining outside, and you are counting the drops on the ceiling, right? Like I don't know where is my microphones. Like you hear like the tap 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 tap
yeah.
tap.
We did hear it.
Yeah, this year, right? Okay, I did it well. So you are, let's say, counting it, and you are getting a histogram of it, like meaning that, like, let's say in this, I heard, I don't know, double taps 10 times. I heard triple taps 20 times or something like that. You are keeping the statistics of it, right? Like this
Mhm.
is, and like when there are different type of noises, different type of statistical distributions, and Poisson is one of a kind. And when you have like that kind of laser, you have that statistics. But now we have something more powerful getting into play. So I told you about like we are creating pairs of photons,
Mhm.
and I know that like if I create the photon from the port A, I know for sure that I'm gonna create a photon at port B. So meaning that there should be a more strong, like the more powerful correlation. They should steer beyond just subtracting light from itself. And this is the exciting quantum part about it. Like because here, when you subtract the light from itself, like you squeeze the noise of the light. And this is called something called quantum squeezing. Like the name is not super, I don't know, creative, but
Quantum squeezing. Okay.
quantum squeezing. So maybe let me give you a fundamental example of quantum mechanics. So most of the people might have heard about Heisenberg uncertainty principle. So Heisenberg uncertainty principle, as you might have heard, says that like if you know the position of a particle with better precision, you know less and less about its speed,
Right.
or and vice versa. So this corresponds to something like this. Let's say you think about like a two-dimensional graph, like the XY graph, right? And like let's say x-axis is, let's say, position, and y-axis is its the speed, right? And in classical world, you can just put a dot, right? Let's say I know that my car is at, I don't know, in Irish Channel neighborhood in New Orleans, which is where I'm right now. And like let's say it's going with like 10 miles per hour. I know that for sure. That's why I can put like a dot with certainty in my two-dimensional graph, right? Like in x-axis, it's Irish Channel coordinate, whatever it is, and at the y-axis for the speed, it is, let's say, 10 miles. But in quantum world, you can't just put a dot. And even if you put a dot, you need to have like some sort of a halo
Hmm.
shrouding it, and that halo shrouding it is something called uncertainty. It's like give or take. Let's say I know that like my car is somewhere somehow in Irish Channel. It's let's say 10, maybe 8 to 12 mile per hour. I don't know for sure. Like it's 10, but like give or take 2 miles per hour, right? There's like some uncertainty around it. And if it is a circle around it, if it's a circle, then it is just like this shot noise, that white noise I was talking about. It is Poissonian statistics, but like once you subtract light from itself, then like you are, let's say you have a panini press, and you take this circle and you are squeezing it, right? Like once you
Hmm.
start squeezing it, it's like it's keeping the same area when you are doing your panini toasts, but like it's getting flatter and flatter, right? Like you squeeze a circle into a ellipse, meaning that like the more you know about the position, the less you know about the speed, or vice versa. So this is where you squeeze stuff, and like in my lab, we are squeezing stuff, and once you squeeze the light like that, you can use this for noise cancellation. Let's say you are trying to detect something with a huge precision. Let's say you are in Ligo, Louisiana, where they detect something called gravitational waves. It requires huge precision, like 10 to the minus 17 meter level precision. And to do so, you need to be canceling a lot of noise. So this is, let's say, one application that can give you Nobel Prize.
Hmm.
Or one other application. What else? Like some companies use it for computation again, to do some certain quantum tasks, also using this squeezing property of light. And recently, this group in China, they did this squeezing experiment on steroids, I would say, because everyone is impressed. They had maybe 50 of the squeezing systems at once, and they are like perfectly choreographed, such that like they performed quantum computing tasks that would take a classical computer, like the top notch, like supercomputer, like 10 trillion years or something.
Whoa.
Yeah, I mean it's a bogus task, like that doesn't have any practical application for now. But like they find like a certain task that would be done immediately with this certain quantum configuration, but that wouldn't be done with a classical computer. I mean, tons of applications just by uh, squeezing the noise of the light.
I have a quick, maybe not quick. I have a question, a fundamental quantum mechanics question to take a
Sure.
step back. So you pointed out, so you mentioned Heisenberg's uncertainty principle, right? The whole
Yep.
idea that if you have these two variables, if you know one with certainty, the more certainty you have of one, the less of the other, right? But you also pointed out that in the classical world, it's not really the way we notice things, right? Like any object that I have in my hand, we can describe it with a linear function, and we don't seem to have that uncertainty. And all these other quantum effects that we know about that you study in your lab, you can go about your daily life and not necessarily see them. So what makes some objects experience quantum behavior and other objects like baseball not to our eyes
Mhm.
exhibit quantum behavior?
This is a very good question, I think, because actually maybe you have like some engineer's guts. Maybe that's why you are asking, because like this is actually where it turns into the engineering.
Right.
Uh, you get the practical implementations through it. So why do we have classicality emerging out of quantumness, right? Like there is some
Right.
eminent classical properties such as like you throw a baseball and you know that it's not acting quantum, but
Right.
it
Right.
is it is there. And even though we are living in a quantum world, so as I told you, like I'm going to be talking from a technological standpoint,
Hmm.
because for all those fancy quantum technologies to work, for any sort of implementation of those concepts, you need to make sure that like you somehow cancel out that classicality. Like the classicality is your enemy. You
Hmm.
need to be. It's called like the quantum coherent behavior or like quantum coherence, and you lose this quantum coherent behavior, and you get something called quantum decoherence. So like the death of the coherence, and you get this because there is the outside world, and since your system, your physical system, your quant and anything since anything quantum, everything is quantum. Your quantum system is coupling more and more to the exterior outside world, the more it loses its quantum magic, its quantum coherence. So
Hmm.
um, I was actually, we are in luck because I was just reading about it. Like I was reading some pedagogical papers uh,
Perfect.
exactly about this phenomena. Because I was also giving some interviews to a Turkish quantum podcast, and they were asking about it. So let's say the most well-known example of wave optics and wave phenomena, and also quantum, is double slit experiment.
Right.
And double slit experiment is exactly like this Schrodinger's cat we are talking about, right? Like the Schrodinger's cat is a two-level quantum system. Let's say it is composed of like scenarios of our cat is dead or our cat is alive, right? Which is just the same as your light or your particle goes through slit A or goes through slit B, right? So you can even do this experiment with water waves. I know like there are some people doing this. This is like this can be seen in any wave. I don't know, any wave configuration, like water waves, sound waves, interference. So let's say you shine light onto the slit and you see some fringes. Okay, you see some fringes, and those fringes are not exactly. If everything was just if light was just particles, let's say,
Hmm.
you would only see two fringes right across the slits. This is the classical or like particle scenario, right?
Right.
But rather you see all those fringes, like you see a central fringe. It's not right across the slit, and then it gets like something called sync pattern. So you see this interference pattern. But the weird part about quantum mechanics is that like as soon as you put a detector onto the slits, let's say you put like something like a photo detector, and it just clicks when it detects light, right? As soon as you detect a click in either of the ports, either slit A or slit B, you are basically killing the cat or keeping it alive.
Hmm.
Then, in 1930s, the original pioneers of quantum mechanics, they were interpreting as something called wave function collapse, meaning that like your physical system now somehow quote unquote collapsed into slit A or slit B or cat dead or cat alive. And because of that, you now lost the quantum magic of it, right? You don't have any interference pattern anymore. And then because of that, since you detected, let's say it's gone through slit B, you only see a mark across slit B. But now the modern interpretation is different. That's why I was saying we are in luck, because the modern interpretation says that it's gonna get very weird. Let me give you a disclaimer.
Mhm.
Modern interpretation says that uh, since we get information out of this physical system, uh, the information is somehow leaking into the environment. How does the information leaks to the environment? Just like you open a can of soda and like the gas just dissipates, right? Like you are just basically dissipating information. How do you do it? First and foremost, like your detector on the slit, which detects which path information, something called which path information. Your light chooses either path. It first, your physical system first couples to your detector. Then also this detector couples to, I don't know, your eye, because you are observing it, right? Or like the computer or whatever. And everything is then coupled to the environment, like whatever there is, like, I don't know, all the outside world. And there is something called quantum entanglement.
Hmm.
And quantum entanglement meaning that like your pets are somehow intertwined, right? Like we have two Schrodinger's cat. When they're entangled, when their paths are intertwined, meaning that let's say one of the cats is dead, for sure that the other one is alive. There are like really strong correlations between them, and you induce that sort of very strong correlations between that original quantum system and the detector and the eye of the observer, eye of the observer and the laptop he is using or she's using, and the I don't know, his room, and yada yada yada. It's weird. Like I was talking about, because like the in the beginning of the talk, I told you in 1990s people were hopeful that they are getting a scalable quantum computer in 10 years, but in 2010 they were depressed and drunk and cynical, uh, because in the 10 years, the reason why they fell into despair is because they weren't able to somehow tackle with this decoherence. They didn't know how to engineer, and they didn't know how to find strategies to decouple from the external world. Because
Interesting.
in the quantum world, external world is your enemy. Because if the universe is observing it, if anything is observing your Schrodinger's cat, it's killing it. You don't want the external world to kill it by simply gazing to it. Just like there is this.
That is so interesting that the universe can see, and that's creating certainty. That's
Exactly.
fascinating.
That's why we have classicality. The reason why we have classicality, because all the Schrodinger's cat are dying or living, instead of just being an interference of that both scenarios. And because of that, like classicality emerges, and they call it like quantum Darwinism, because like at the end we have classicality emerges because like all those cats are living, dying, etc., etc., and then like this emerges out of it. This classical world we are. It's an epistemological nightmare. I know. Who was it? Who was asking about like if there's a think about the forest and if a leaf falls, but no one is observing that leaf falls, does it really happen? Right? It's one of the English empiricists. I forgot.
Yeah.
It's basically like that. It's like super philosophical, but like the weird part is like all those super philosophical questions are actually engineering questions at the end. You can reformulate as an engineering question, and this is the engineering of 21st century. Like, how are we going to isolate from the environment? How are we going to isolate our system from everything so that it keeps its quantum magic, so that the gaze of the universe, gaze of our measurement devices, our gaze itself doesn't kill the good stuff.
Do you consider yourself an engineer in that sense, or are you a scientist?
Uh, I think I'm something in between. I'm
Mm.
more like I would say I'm more like a statistician
Ah,
and computational. Yeah, computational scientist is like a bit better term. So I'm because like I'm also doing like data analysis, and so there's like some sort of I would say dialectical interaction of all those stuff in my field. So you make some observation and you use those observations to better design your experiment so that you know where to look better, and then you use those information to again make some simulation, and then use those simulation to again make an observation. So it's some sort of like a very dynamical process of like simulating and observing, simulating and observing. So yeah, there is both an engineering aspect to it and very theoretical aspect to it.
So, one thing we often ask, and I'm wondering, is you talk about the last 10 years, and but where do you see this going in the future, and how is it going to be more beneficial to society on the whole, moving forward, maybe in the short term and in the longer term?
yeah.
Uh, Very good question. I mean, even if you just check like the job postings and like the I don't know, like the those listserv emails that sends you I don't know recent events and conferences and like the job postings again, you see that like the some things are changing. So for starters, like the reason why these technologies are going to be so beneficial is that like this quantum stuff already lives in uh, I would say some matrix work, not the movie Matrix, but like the this linear algebraic construction matrices.
Right.
Anything you are doing, let's say you are designing a plane. My best friend, like he makes his living through selling fluid dynamics software to I don't know plane companies, etc. Because like they need to be keep solving, let's say this fluid dynamics equations like Navier-Stokes, etc. Uh, for the aerodynamics, right? Or let's say, and it involves like many matrix multiplications and like solving matrix systems of equations.
Mm-hmm.
Also, let's say you are designing drugs, right? Drug design. During my internship, like I were collaborating with some people doing that kind of stuff. Like the quantum computers are going to accelerate it because they're gonna accelerate like all those hitherto classical molecular dynamic simulations. There are already some companies. For example, there's Boston-based Zapata Computing, and there's like I don't know Rigetti Computing, I think Philadelphia based. Uh, there are many companies like that. There and like I think there's Atomwise also somewhere Boston. They are already working on how to implement these techniques to design, let's say, molecules and like the drugs and everything.
Huh.
What else? Finance. I yesterday, for example, I saw like some quantum finance a job posting in Paris and like some in New York City, because like they are trying to find that, yeah, let's say you are trading stocks, and then like it involves like lots of buying and selling and lots of data fitting into time series. And if you have like this I don't know, this science, sci-fi level computer that does some certain tasks very well, this is one of the tasks that's on high demand. Like it's gonna accelerate artificial intelligence, for example, and a lot. I mean, it's like a whole different genre.
I just want to say I love the way you put into context the question by looking at job postings, because that those are real. Those are people who are can go do that and get paid for it and professionally do it full time.
Well, there's
That's
companies that think it's worth spending the money on too.
Yeah, and I think that's another interesting thing about this field is, Honor, you noted, really, some of the biggest companies and nations and governments in the world are really trying to put resources into this to try to make it happen. Uh, as I think as foreign as it might sound to some people, that's all proof that this is real and this is accelerating,
Hmm.
uh, which is exciting for me.
Exactly, proof of concept.
Yeah,
Yeah, seeing is believing. Like if you
it,
don't see it, you don't believe it.
yeah. One other question I really like to ask this question, but in general, what gets you most hopeful and excited about the future? And also, what gets you most concerned about the future? And again, this could be pertaining to this topic or anything else. We've had lots of answers. So, what are your thoughts there?
Um, that's a good question. I see that all these new technologies, especially in, I don't know, like in the regarding artificial intelligence and quantum computing. I mean,
Yes.
I'm telling it because like these are my fields that I'm using. I'm seeing that like it's going to accelerate a lot of stuff. Like Google Brain team, like one of their AI teams. I think just a month ago they tackled a protein folding problem using deep neural networks. And I know a lot of people who've been working on this for their whole life, and they hadn't have any progress. But like they just basically solved this holy grail of I don't know, all this biophysics. It's
Wow.
going to make some huge impacts in like I don't know, cancer research and like I don't know, again, like drug design, everything. And like and also like we're gonna use like the quantum computing and like various other technologies to just like we were telling about, just like we were contextualizing before, for many discoveries. But I think like what's making me concerned about it is like is policy wise.
Hmm.
Like they are coming, they are up and coming, but like I don't know like how the society is going to adjust that. So like instead, like uh, before we should concern ourselves about like I don't know, like the Terminator level uh,
Uh oh.
advantage of the artificial intelligence. I think like what we should concern ourselves more about like the I don't know, my old grandfather, he was a truck driver, for example. And I know that like with artificial intelligence, like even like when I was taking like some toy projects about self-driving cars, and I don't know, like, they're gonna lose job. And like I know like in United States there are like more than a third of jobs are just driving related.
Hmm.
And there's gonna be a huge problem on unemployment. And I don't know, like we have like we both have the cure and the poison at the same time. So And the reason why, I mean, it can be cured because they are marvelous technologies, but they can be poisoned because it's the work of the policymaker now. So like, how are they going to use it? So this is
Interesting.
what concerns me most, and I'm not gonna go to climate change because it's making me too dreadful and anxious. But
Um,
yeah.
I that's it's good to hear coming from you though, that these concerns, because I think it's easy for us to get too excited about possibilities and not think about how to do things right. Because we do want to do things right
Mhm.
in the right way, if at all possible. Um,
Th- That's why they shouldn't abolish, I would say, humanities in colleges. I think because I don't know, like let's say if you are a genetics researcher, I think at some point like you should get a course on ethics and like stuff like that. So we can't be just blind to it,
Yeah.
and like let's say the societal biases in machine learning algorithms of stuff like that. So we can't just turn blind eye to that. So they are both marvelous, but like if you but they possess like such a huge power, right? So I think Oppenheimer, after the first atomic bomb was
mhm.
shot, like he was quoting this uh, Hindu text saying that yeah, now I became the I forget about it, like the quote, but like he realized like what kind of power he unleashed. So we should be always
It was something about becoming a god or something. I can't remember exactly,
something
but
like that. Like I became
I
death or
believe
something like that. Something really powerful and dramatic. But yeah, I mean, there's a
yeah.
reason why he was dramatic.
Another thing we love to ask about is, what advice would you have to a younger person interested in doing what you do? You mentioned you've got a younger
Yeah,
brother, or what's
my
some good
younger
advice
brother
for
is
someone who
becoming a
wants to
biologist, and like even
do
though
what you
I was pushing him in different directions, but yeah, I'm glad. So, but for example, like I keep telling him to learn Python, and the newer generations I think much more lucky in terms of resources. Like there's everything in YouTube. I mean, it's easy to get distracted too. I know, but like I mean, just Google quantum computing, or like just go to YouTube and quantum computing lectures, or like quantum optic lectures, machine learning lectures. There are a lot of good materials, or like they can just take an online course from Udemy, Coursera. I took a lot. I'm still taking, and I know a lot of people in like industry and academia. There's it's non-stop learning because like times are keep accelerating. Even though like I am over 30 now. Like I need to just keep up with the new knowledge. Like,
Mhm.
and I think they are lucky with their younger, more plastic brains comparing to me. They will be if they let themselves just uh, exposed to all this good material. I think it's gonna make a difference.
I mean, it's so much of the advice that the people on our shows have give. It's not only for this particular field. I think that goes for anyone who wants to do anything. Is be be resourceful and taking advantage of this content that's everywhere now. There's even podcasts out there on the topic. So I hope some of you will listen to this podcast who are interested in the topic. James, you got anything else?
go ahead.
Ah, Honor. I'm going to ask you my favorite question, the
Okay.
most important question. What is your favorite pizza topping?
Oh,
Yeah.
That's a good question. I like it very plain, actually. Like I like it that when the dough is very good. Like
Mm,
they took their time just fermenting it, like very good flour. I'm super into just cooking and doing pizza and focaccia all the time. That's why I'm super excited about this question. So I just like it like very plain, like Napoli style, like Neapolitan pizza. Uh, just maybe fresh mozzarella, really good like fresh tomato, or like maybe from the can, like what was San Marzano tomato or something. I think
mm.
they just crush with the hands. Oh, so good, and like fresh basil.
It's important that the bread is good, though.
Oh yeah, it's all about the bread.
Yeah.
It's all about the bread.
In my opinion, Honor, that is the correct answer. For me personally, I don't. I prefer no toppings. Just like you said,
The sauce, the cheese, and a little basil.
that's
Yeah.
Yeah,
that's perfect. That is wonderful. What a purist. That is,
yeah.
that is, and you said you make your own?
Oh yeah, I have a lot of bruises because I have the pizza stone and like the shovel, and sometimes like I turn on the broiler of the oven and like it hits me when I'm like not careful while trying to put like things with the shovel, and
Now,
I always had like scars everywhere on my
now
arm because of that.
I have a question. What I always heard is to cook the pizza right, you need a very high temperature
Mhm.
heat source that's typically higher than a normal kitchen oven. Do you just use the normal kitchen oven, or do you have a way of getting to a higher temperature?
Really good question. I mean, they get like this very powerful oven, yes, but like let's say it goes to maybe 700 Celsius or some at some points. I don't know in imperial measures,
Well,
sorry. But like they don't most of the time like put the bread straight to the hottest place, but like
Mm-hmm.
mostly like they want to control it, like they just put it. I don't know, maybe to the spot where it is like 500 Celsius or something. Still
Mm.
not achievable by our ovens. But the point is this. So first, you got to have like a very good pizza stone, and you let it absorb the heat for 20 minutes.
Ah, okay.
And then also it's important that like you put like water in a metal bowl or something so that like it creates like the steam in your oven.
Mm.
no,
Okay.
Uh, and then you turn on the broiler, and then like once it's like super hot, the stone is super hot, you turn on the broiler, you shove the pizza, uh, close the lid, then you take it back, just turn it, put it back again, maybe one more minute, and then you take it. So
That's it.
exactly.
Fantastic.
we had a previous guest who said that he makes his own pizza because nobody can make good enough dough at any pizza place he goes to. This is the second time I've heard that the dough is more important than any
The,
other part.
it's very important. I personally think the sauce is the most critical, but I admit the dough is very important. Um, Honor. Okay, the last question. For any of our listeners out there who want to follow you, is there anywhere that they can go? Social media, websites, anything like that you can point them to?
uh, I mean, I'm planning to open a blog, but for now, they could just follow me on Twitter or LinkedIn. Just type my name, Onur, Onur, and my last name, Danaci. You're gonna probably see in the description.
Yep.
And I'm happy to just answer any of your question. Like I love inquiring minds.
Yeah, and I'll say this to everyone. I mean, I always remember Honor, and you continue to be this way. You've always been really generous and thoughtful with questions for people who have questions about your topic. So thank you for that. Thank you for being really generous and descriptive with us. And I'm sure if anyone has any questions, you'll be happy to
I would say
follow
it's
up.
my mother, so like she's a teacher, and like she's always
Yeah,
super patient about like the questions coming from kids. So I think she just gave this, I don't know, uh, this ultra pedagogical upbringing.
Well, it's been great, and we'll say thank you, and thank you to the listeners for tuning in, and
Thank you for hosting me.
Thank you.